Alrighty, good afternoon, everybody. Hopefully you had a chance to get settled and give this question a try. Given the following decomposition reaction, calculate the moles of oxygen gas produced from 5 moles of hydrogen peroxide. Whenever we're working these problems, you always want to start with rephrasing the question. Our given information, we have 5 moles of hydrogen peroxide. We need to figure out how many moles of oxygen gas that makes. To do this, we have to use a mole ratio. The two compounds we're interested in are the hydrogen peroxide and the oxygen. From the balanced chemical equation, you write the mole ratio. So you read the numbers in front of the compounds as moles. For hydrogen peroxide, it would be 2 moles. And we write these ratios as fractions. 1 mole of oxygen gas. When there's no coefficient written in front, you write 1 mole. The second ratio is just the reciprocal. You write 1 mole of oxygen gas on top, 2 moles of hydrogen peroxide on the bottom. So that's the refresher on how to write our mole ratios. Then we set up the problem. Starting with the given information of 5 moles of hydrogen peroxide, we have to choose one of these mole ratios. Which one do we have to use if we need to convert from moles of hydrogen peroxide to moles of oxygen gas? Is it A or B? We're going to use B. And before you do any math, always make sure that you double check that your units cancel out. So we're left with moles of oxygen gas, and that's what we want. When you put this into your calculator, this is a much more simple problem than the ones we were doing last week, but we'll get there. You just do 5 divided by 2. So you should get 2.50 moles of oxygen gas. How did we do on this question? Let me know in the chat. Did you get it? If you didn't have a chance to do it, does it look like, yeah, I remember that from last week? Let me know. Well, hopefully most of you remember. Remember, it's okay to put in the chat that you don't remember or you need a refresher or can we go over that again? Because I'm here for everybody, not just the people who get it. So, like I promised, yeah, it's okay. Like I promised, the next part of class is going to be kind of a refresher. So we went over mass-to-mass stoichiometry problems last week. I'm going to show you this example. Feel free to kind of look through your notes and try it ahead of me, if you're looking at the problem and like, I don't know about this, then you can just stick with me and kind of watch it and get reacclimated to what we were doing last week. So it's totally up to you at your own pace. I encourage you to try it. If it looks like something you can tackle, go ahead and tackle it. Otherwise, I'm going to just rule through the whole thing. What is the mass of zinc oxide that can be prepared from 1 gram of zinc metal? So we always care about what the question is and what our given information is. Those are the two things that I highlight. The given information, we have 1 gram of zinc metal. What we're trying to find is the mass of zinc oxide. Now, if we didn't have the luxury of a title that says mass to mass, you could then say, okay, I've got mass on one side. That's my given. I'm asked about a mass as my question, so this has to be a mass to mass stoichiometry question. Let me know if you're with me so far, because that's one of the biggest issues, is just identifying what type of problem we have on hand. So are we good so far? Sure. So I looked at the given information in the question, and I said, all right, I'm given grams of zinc, which is a mass. And my question is, what is the mass of zinc oxide? So that's another mass. That makes this a mass-to-mass question. We're taking the mass of the given, converting it to the mass of our unknown. That help? You're welcome. So now that we know what type of problem we have, we know the generic plan to use, and I'm going to rewrite what I did last week with our A and B to give you the generic plan for how to solve a mass-to-mass problem. We start with grams of A. And in this case, our A is zinc. And I'm going to rewrite the plan using zinc and zinc oxide in a second. But I'll assign A and B now. We take the grams and convert to moles. We always need molar mass for that. The second step is to convert moles of A to moles of B. In our question, zinc oxide is the B. That's the unknown. We need to figure out how many grams of zinc oxide we make. We need a mole ratio for that. And the form that it's going to have is the amount of B over A, and that comes from the chemical equation. The mole ratio is like what we just did in the do now. You use the chemical equation, you write it out as moles, and that's what you use to get from A to B. The last part of the equation we're going to set up is to go from moles of B to grams of B. We need the molar mass of B to get that done. Now let's make it more specific for our problem. So this was the generic one. And it is hopefully in your notebook from last week. Now we'll write the plan with our actual information from the problem. We're starting with grams of zinc. We first have to get to moles of zinc, and we need the molar mass for that. You look on the periodic table, you see what it says for the atomic mass, you write it in grams. The next part of our plan involves converting the moles of zinc to moles of zinc oxide. That means we need our mole ratio. B over A. Our B in this case is zinc oxide. The A is zinc. When we get to that part of writing the equation, we already know what we need. We just put it in the right spot. Then we convert moles to grams. Again, we're using molar mass. For this, we've got 2 elements in our compound. So remember, with molar mass, you look up each element on the periodic table, you add them together, and that's your molar mass. Now, for the sake of time and making sure that you understand how to do the problem, I'm writing in the molar masses. But on your homework and for the exam, and when we do our exam review, you will have to be doing all of the calculations of the molar mass and everything else. So make sure that the chapter 8, how to calculate molar mass, is good for you. Do you have a question? Okay, so I can write it out for zinc oxide. I think somebody has their mic on. So the molar mass of zinc oxide, you look up zinc and you look up oxygen, and then you add them together. So that's our plan for this problem specifically. Now we're going to put the real numbers in. You're very welcome. We started with 1 gram of zinc. If you're into colors like I am, stoichiometry, this whole chapter, have your color pencils and your markers or your highlighters, whatever you use, because we're going to be doing the same thing this week. First step, we have to convert grams to moles. That means we need a molar mass unit factor. 1 mole of zinc at the top, grams of zinc in the bottom, and that will get us to moles of zinc. Now we have to write our mole ratio. Zinc oxide over zinc. Go back to the chemical equation. We have a 2 in front of zinc oxide, so that's 2 moles. We look at the zinc in the chemical equation. It's got a 2, so we write 2 moles for that. That's our mole ratio. Then we need to write in our molar mass again, but it's for zinc oxide this time. We put the grams in the top because we want to convert from moles to grams. And I'll show you how it all cancels out. Grams of zinc cancel, and we have moles of zinc. Moles of zinc cancel. We use our mole ratio. We get moles of zinc oxide. We cancel those moles, and we get grams, which is what we want at the end. To put this into your calculator, remember that parentheses are your friends. Now for our mole ratio, we have 2 over 2, and that equals 1. So I'm going to write it out here. 2 divided by 2. But that's 1. So if you don't put that into your calculator this time, it's fine. But make sure that you know when you do and when you don't if you're going to play that game. To be safe, always multiply everything all the way through. So that's what you should put into your calculator. Try it out if you haven't already, and let me know what you get. That is exactly what I got. Should be zinc oxide, not zinc. But I knew what you meant. So let me know if there's questions here, or if we're ready to move on to continue our recap. Questions, or are we ready to move on? You know I like my feedback. Okay. Next, we're going to recap mass to volume. So again, feel free to move ahead of me, do the problem. Otherwise, stick with me and we'll do it together. What is the volume of oxygen gas needed to fully react with 1 gram of zinc metal at STP? We always rephrase the question. I'm starting with 1 gram of zinc. The question is asking for the volume of oxygen gas. Grams of zinc, that's a mass. It's asking specifically for the volume. So we know this is a mass to volume question. First, I'll put up the generic how to solve it for mass to volume, just like I did with the mass to mass. We're starting with grams of A. And zinc is our A in this case again. We need to get to moles. That's always the first step. Take what you have and get to moles. Our next step is get to moles of B. And our B in this problem is oxygen gas. That's where the mole ratio comes in. in the form of B over A. Doesn't look too different from last time, but here's where it changes. We need to get to a volume, which can be liters or it could be milliliters. So make sure to read the problem. If it doesn't specify, liters are fine. Otherwise, make sure you answer with the correct units in the problem. To go from moles to liters, we have to use molar volume. And that is a chapter 8 concept where we said 1 mole of gas is equal to 22.4 liters. From that unit equation, we can write out unit factors, and I'll show you which one we use whenever we're doing mass to volume. So stay tuned. Now let's make it a little more personal. We'll put in zinc and oxygen in place of A and B. Just like last time, we're starting with grams of zinc. And when you're doing this for your homework, you don't have to write out the generic plan every time. I'm just doing that as a reminder. But if it helps you, go for it. We need the molar mass of zinc, which I'll write again. From there, we get to moles of oxygen gas. Our B this time is oxygen gas, and our A is zinc. Then we want to get to liters of oxygen gas using molar volume. And I'll show you again which unit factor we use for that. Let's put the whole equation together. First, we deal with converting grams to moles with the zinc. Then we deal with the mole ratio. We said it would be oxygen gas over zinc. Here's oxygen gas. There's no coefficient in front, so that means I should write 1 mole. With zinc, there's a 2 in front. 2 moles of zinc. For molar volume, we can write 2 unit factors from our unit equation. One mole over 22.4 liters, and 22.4 liters over 1 mole. Which one should we use, A or B, if we're trying to go from moles of oxygen gas to liters? We should use B. Whenever you're doing mass to volume in that order, that is the unit factor that you use. 22.4 liters over 1 mole. Then, as always, convince yourself that you have everything arranged properly by making sure your units cancel the way you expect them to. We get to moles of zinc, moles of oxygen, liters of oxygen. In your calculator, parentheses are your friends. So that's one way to enter in all these numbers into your calculator. And when you do that, you should get 0.171 liters of oxygen gas. So you can always, if you're having trouble with your homework and you're like, man, am I doing it right? You can go back to these problems and make sure that you're entering the numbers into your calculator properly. So this is a way to help you kind of format it when you're doing your homework with Mastering Chemistry. So how do we feel about these mass to volume problems? Does it kind of ring a bell? Good, good. So now we're going to get into the new material. We left off last week with we did mass to volume, and then I showed you a volume to mass example. So that's where we're picking up. Again, if you feel comfortable, go ahead and try it. But we're just going to work through one volume to mass problem. It's just kind of flip-flopping where things go in our plan. But the overall strategy is still very, very similar to mass to volume. How many grams of sodium chloride are produced when 9.21 liters of oxygen gas is produced at STP? Let's rewrite the question. We have 9.21 liters of oxygen gas, and we need to figure out some mass of sodium chloride. If you didn't have the advantage of the title telling you what type of problem it is, you would say, okay, 9.21 liters, that's a volume. I'm looking for grams of sodium chloride. That's a mass. That makes it a volume to mass question. And what I'm going to do for this one is I'll give you the generic how we solve it. Then I'll give you a couple of minutes to write out the plan specifically for this problem and try to set up that equation. So here's the generic how to solve it. We're starting with liters of A. We have to get to moles of A, and that's got to be with molar volume. We're at STP, so we're allowed to do that. The second step in these problems is always using a mole ratio. And that's going to be the form factor of B over A. What we don't know, the unknown, over what we do know, which is A. Then we get to grams of B using the molar mass. That's the generic plan. I'm going to give you 3 minutes to fill in the plan with the details from this problem and try to set up the equation. If you have questions, you can go ahead and put them in the chat or ask, but I'm going to give you 3 minutes for you to try it on your own. If you haven't gotten to an answer yet, that's okay. I'm going to start writing here just the plan so that if you're stuck, you might get unstuck. Our A in this case is the oxygen gas, and our B is the sodium chloride. So I'll give you the molar mass, just so that you don't have to do the work if you haven't already gotten there. And remember, you just look up sodium, you look up chlorine, you see what those masses are, and you add them together. That gives you the molar mass of sodium chloride. The first step, we're using molar volume to get from liters to moles. Our options, we've got 1 mole over 22.4 liters and 22.4 liters over 1 mole. We need to use the one with moles on top. And if you're going from volume to a mass, you will always use that unit factor, 1 mole over 22.4 liters. Next is the mole ratio. What do I need to put for my mole ratio? You can put it in the chat. You don't have to write, the moles of this and that. Just give me the numbers as a fraction. What's my mole ratio for this problem? And if you need a hint, that's your hint. Yeah, so we're going to put the moles of sodium chloride on top. And that comes from the chemical equation that is balanced. And the moles of oxygen gas on the bottom. Then we use the molar mass. We put the grams in the top. and 1 mole on the bottom. Convince yourself that you did it right by doing unit analysis. We get moles of oxygen, moles of sodium chloride, grams of sodium chloride. For entering this into your calculator, I'm going to write it above this time. Always make sure to use parentheses. It just makes sure that the calculator does all of the operations in the order that you want. Calculators are smart, but you're smarter. When you do all of that, you put it into your calculator, you should get 16 grams of sodium chloride. That's volume to mass. Let me know if we have any questions here. I'm going to linger a little bit, make sure that you have a chance to get it all down in your notebook just in case. But as you do that, let me know. How are we doing so far with these stoichiometry problems? And if you're kind of sitting in the background, kind of taking it all in, this is my check-in time. Let me know that you're with me. You say, hey, Dr. Hefner, I'm here. I'm with you. It may still be shaky, but I'm here. Just want to see how everybody's doing. And much appreciated. I know the style for everybody isn't the same. Everybody's not going to catch on at the same rate for every topic. Not always going to have the answer. Sometimes you're just going to sit on your hands like, I'll wait this one out. And that's totally fine. I just want to know you're with me. So thanks for participating. So far, we've covered mass to mass, mass to volume. We also did volume to mass, which is still under the same umbrella. Now we've got to do volume to volume. And this is the easiest one so far. It's a very exclusive club. It's for gases only. So I'll show you how we do it. This is the example problem from the video. So if you watch the video, it will look familiar. Let me get my highlighter out. How many liters of oxygen react with 37.5 liters of sulfur dioxide in the production of sulfur trioxide gas? As always, restate the question. That helps you identify the problem type. The given information is 37.5 liters of sulfur dioxide gas. And this is again where that chapter 6 knowledge comes in, because you need to know the difference between sulfur dioxide and sulfur trioxide. We're trying to figure out how many liters of oxygen gas we make, or how many we need, excuse me. When we're doing volume to volume, we only have to write a mole ratio. But instead of using moles, you can use volume in liters. So if we're looking at the relationship between sulfur dioxide and oxygen gas, then we can write two relationships here. The first relationship, 2 liters of sulfur dioxide gas for every 1 liter of oxygen gas. The second relationship is just the reciprocal. From here, we're ready to set up our equation. And I know you're probably like, wait a minute. So you're not going to write out stuff like a plan for 5 minutes? No, volume to volume is that easy. You write out your ratios, you set up your problem. If I need to convert from liters of sulfur dioxide to liters of oxygen gas, am I using A or B for my ratio? Yeah, thank you. You fill it in. Make sure that your units cancel. We're looking for liters of oxygen gas, and that's what our units will leave us with. In the calculator, you're just doing 37.5 divided by 2. With sig figs, you need 3. You get 18.8. And our units here are liters of oxygen gas. Questions? Or are we ready to try one for ourselves? Because I've got some more problems for you to try. Then let's move on. I'll set up the problem with you, and then I'll give you a couple of minutes to solve it. How many liters of sulfur trioxide gas are produced from 37.5 liters of sulfur dioxide gas? Here's our given information. The same 37.5 liters of sulfur dioxide gas. You need to figure out how many liters of product you make, which is sulfur trioxide gas. Write out your ratios, set up your equation. I'll give you 2 minutes, and then I'll start writing things in. I'm just going to write out the ratios, just in case someone is stuck. These are the 2 compounds we're interested in. We represent them as liters with the coefficients out in front. So those are our 2 options for setting up this equation. Am I using A or B to get from sulfur dioxide to sulfur trioxide? Make sure that your units cancel, as always. And that's what we're looking for, liters of sulfur trioxide gas. Well, 2 liters over 2 liters, that's 1 over 1, right? So no math really necessary here. That's our final answer, 37.5 liters of sulfur trioxide gas. How do we feel about volume to volume? Good. All right. So I've got one more problem for you to try. And then we'll take a vote on whether or not we want to take a break after this problem or just keep pushing on. So try this problem. I'll give you a couple of minutes to set it up. We'll go over it, and then we'll figure out where we're going from there. So think about your answer while you're setting up the problem. I'll check back in 2 minutes. Here we go. This time I let you completely set up the problem, so we're going to start by reading and setting up the question. Then we'll write our ratios. How many liters of oxygen gas are required to make 15 liters of sulfur trioxide gas? Our given information: 15 liters of sulfur trioxide gas. We're trying to figure out how many liters of oxygen gas we need to actually make that amount. These are the 2 compounds we're interested in. Now we write our ratios. There's no coefficient in front of the oxygen, so we write that as 1. Two liters of sulfur trioxide. Then the reciprocal. So this time, we need to have sulfur trioxide in the denominator. That means we're going to go with the first one. In your calculator, you're doing 15 divided by 2. And when you answer, you need 3 sig figs. So your calculator will stop here at 7.5. But you need to add a 0 so that you have 3 significant figures. And don't forget units. How do we do on that one? Good. I'm glad. So if you're not doing well, that's okay. I always post the notes. You can rewatch the video. You can go to the pre-recorded video, office hours, one-on-one, so you know how to reach me. Make sure that you reach out. If stoichiometry is difficult for you, I don't want you to just sit in the background and worry. I'm here for you, so don't forget that. Now we're at a crossroads. Let me know if you want to take a break or if you want to keep trucking and we end class a little early. We got to vote for keep going. So if you don't feel that way, 2 votes. It's going to get harder. We got 3 keep goings. So we're going to keep going. If you need a little break, if you need to shake your brain out, that's fine. Take a breather. It's the internet. I won't know. It's really okay. So we've got 2 more concepts to cover. We're going to do some practice problems with both of those, and then we'll be done. Limiting reactant. Let's say you're making a grilled cheese sandwich. Now it's 3 o'clock. Hopefully you've had lunch by now. But say you didn't, and you were dreaming of a grilled cheese sandwich. The most basic sandwich, 2 slices of cheese, 2 slices of bread. If you come to me and say, here's a sandwich with 1 slice of cheese on it, I'm going to look at you sideways. That doesn't even reach the edges of the bread. It's got to be 2 slices. We can write that as an equation. 2 slices of cheese, 2 slices of bread, you make 1 sandwich. Let's say that I have 4 slices of cheese and 4 slices of bread. Simple question, how many sandwiches can I make? I can make 2. I just doubled the amount of ingredients that I have, so I can make 2 sandwiches. What if I have 4 slices of cheese and I've got 8 slices of bread? How many complete sandwiches can I make? Still 2. All right. We're not changing the ratio of cheese to bread, which is what I would do. You know, I have kids. Sometimes you got to make things stretch. But in chemistry, we can't do that because then it's a different reaction altogether. So we have to keep the same ratio of cheese to bread. Even though we've got all this extra bread, we can only make 2 sandwiches. In this example, our limiting reactant, which I abbreviate LR, is the cheese. We've only got 4 slices, and that's enough to make 2 sandwiches. So that's what we make. The bread, however, we've got plenty of bread. That's in excess. This is the same concept that we're going to use when we're looking at chemical equations for real. Hopefully I didn't make you hungry talking about grilled cheese. It's one of my favorites. Grilled cheese, cup of tomato soup. That's like classic Panera bread right there. Anyway, let's apply the same concept. So limiting reactant. It's the one that controls the amount of product that you make. It gets used up before all your other reactants. And sometimes in the lab, in a real world scenario, maybe you have a reactant that's really expensive or it's really hard to make. So you have to make it yourself in the lab you only have but so much of it, that's going to limit how much of your next reaction you can do. So doing these problems, you absolutely need to know how to use them if you're going to do chemistry in the real world. Here's an example that I'm going to go through with you guys. This is a limiting reactant problem. We have to figure out what the limiting reactant is and how much product we're going to form. Just like with the other stoichiometry problems, you want to read through the problem and identify what type of problem it is. And I'll show you how to identify when you have a limiting reactant problem. If you heat 5 moles of iron and 3 moles of sulfur, how many moles of iron 2 sulfide are formed? Notice that with this problem, we're given 2 amounts. We're told how much iron we have, which was 5 moles. And we're also told how much sulfur we have, 3 moles. We don't know how much iron 2 sulfide we make. When you're given information for more than just one reactant, that means you have a limiting reactant problem. You're mixing these ingredients and figuring out how much you'll get at the end. To attack these problems, you have to do 2 stoichiometry problems. In this case, the first problem that we have to do is figure out if I had 5 moles of iron, how many moles of iron 2 sulfide will I make? The second question, if I had 3 moles of sulfur, how many moles of iron 2 sulfide will I make? And we're assuming in both of these scenarios that we've got, this reagent and excess of the other. We always use the same format of B over A. The A is our iron. The B is the iron 2 sulfide. You look at the problem. There's 1 mole of iron 2 sulfide for every 1 mole of iron. That means we would make 5 moles of iron 2 sulfide. But we're not done. We now have to look at how much iron 2 sulfide we would make if we just had the 3 moles of sulfur. One mole of iron 2 sulfide still goes on the top because that's still our B. But our A in this case is the sulfur, and there's 1 mole of that in our chemical equation. So we figured out how much we would make with the 5 moles of iron, how much we would make with 3 moles of sulfur. Next, we asked the question, which reactant forms the least product? So which one is smaller? The 5 moles of iron 2 sulfide or 3 moles? Yeah, it's going to be the second one. 3 moles. And that means that sulfur is the limiting reactant. So the form for all of these limiting reactant problems is you have to identify one that is limiting reactant. And once you know that, you do a stoichiometry problem to figure out how much product you would make using each piece of given information individually. Then at the end, you ask the question, which reactant forms the least amount of product? That's the one that you'll make. So let's go and do another example where instead of it just being a simple mole ratio, we're actually adding on top the stoichiometry problems that we were just going over. So this is the example that I did in the video, but I'm going to break it down for you again here just to make sure that you really get it. And then we'll do some examples. I think I have one example after this. How much molten iron is formed from the reaction of 25 grams of iron 2 oxide and 25 grams of aluminum? We're given 2 pieces of information. That means it's going to be a limiting reactant problem. We've got to figure out which one of these is going to make the least amount of product. I've got 25 grams of iron, 25 grams of aluminum, and I have to figure out how much iron. So when they say how much molten iron, the assumption here is that it's mass. I'm starting with mass. My question is asking for a mass. So that means this is a mass-to-mass problem coupled with the limiting reactant concept. So I'm going to have to do 2 mass-to-mass problems to figure out which one of these is my limiting reactant and how much molten iron I'll actually make. I'm not going to go through and write out the plan this time. I'm just going to write out the 2 equations. If you want to go ahead and write it out yourself, go for the gold. If you want to write out the plan in your notebook, you can leave some space for that and then go back and write out the plan to convince yourself that you understand. So the first problem we're going to do is taking the 25 grams of iron 2 oxide and converting that to grams of molten iron. First, we convert to moles. In this case, you would have to calculate that molar mass. And it would just be taking the iron plus the oxygen off of the periodic table. Then we have the mole ratio. Our B is the iron. A is the iron 2 oxide. Finally, we need the molar mass of iron to get to grams. Make sure those units cancel. This is how you would put it into your calculator. So notice how the ratio is 3 to 3. You can put that in there, but it equals 1. So whether you put it in or you don't, you should get the same answer. If you are a creature of habit and you just want to put it in there just so that you always put it in there, do it that way. So for the first problem, if we had 25 grams of iron 2 oxide, we would make 19.4 grams of molten iron. But that's not it. We've got to do that again, only this time with the aluminum. Starting with the molar mass. For aluminum, you just look it up on the periodic table. Then we do that mole ratio. Not that one. This time we care about the aluminum and the iron. The B is still iron. A is our aluminum. Then finally we put the molar mass of iron. Make sure all the units cancel. In your calculator, this is what you'll put. Always use parentheses. They are your friends. When you put all of that into the calculator, you get 77.6 grams of iron. But we're still not done, because we need to determine which one of these will actually make. which reactant forms the least amount of product? That's the question that we always have to answer. And our equation in 1 gives us a yield of 19.4 grams of iron. That means the iron 2 oxide is the limiting reactant, and we make 19.4 grams of iron. So that was kind of long, right? We had to do 2 mass-to-mass problems and then figure out which one of those we're actually going to make. But let me know if the concept makes sense. Let me know how we're doing here. So I have one for you to try. It's not a mass-to-mass problem. It's a volume-to-volume problem. So it's a volume-to-volume limiting reactant problem. I want you to try to set it up for yourself. I'll give you about a total of 5 minutes. At about 3 minutes or so, I'm going to check back in and start writing because it takes me a while to set up the questions. So 5 minutes total, thereabout. But at 3 minutes, I'll start writing. I'm going to start setting up the problem here. So if you got stuck, you can get unstuck. How many liters of sulfur trioxide gas are produced from 18 liters of sulfur dioxide gas and 18 liters of oxygen gas? So if we didn't have the title of limiting reactant problems, we would say, okay, I've got given information for 2 reactants, and I need to figure out how much product. So that means this is a limiting reactant problem. Let me switch back to black here. And now I need to figure out what type of stoichiometry problem I have. So I rephrase the question. I'm taking 2 reactants in these volumes and mixing them together. How much or what volume of SO3 will I make? Well, I'm starting with volume in both cases. And the question is asking about how many liters, which is a volume. So that makes this a limiting reactant volume-to-volume question. We're going to have 2 equations that we need to make. The first is going to deal with the 18 liters of sulfur dioxide gas. We're going to figure out how many liters of product we make. Then we figure out if we have 18 liters of oxygen gas, how much product do we make? Then we ask the question, which reactant forms the least product? So that's the breakdown of the plan for how we're going to attack this thing. Our first one, we're looking at SO2 and SO3. That's going to be our ratio. The B is SO3, the A is SO2. We put B over A. The relationship is 1 to 1, so we don't even have to touch our calculators here. 18 liters of SO3. We do the same thing with the oxygen gas. Oxygen is our A, SO3 is our B, here is how we write the ratio. Still have the SO3 on top. And the oxygen goes on the bottom. When you multiply 18 by 2, you get 36. Then we have to look at which reactant forms the least amount of product. $18 is definitely less than 36. So we're going to form 18 liters of sulfur trioxide gas, which means that sulfur dioxide gas is a limiting reactant. So how do we do on that one? All right. So make sure that you know how to do each of these stoichiometry problem types, because you can see them all coupled together. Limiting reactant along with a volume to volume or volume to mass, any of the ones that we've covered. One more concept, and that's percent yield. In the real world, when you're in the lab, you never make what you expect to make, okay? The amount of product that you actually make is called the actual yield. That's determined experimentally. It's always given in the problem. The amount of product that you can calculate through any one of those stoichiometry problems or limiting reactant problem, that's called the theoretical yield. So all these problems that we've been doing for Chapter 9, that's calculating the theoretical yield if we were to mix A and B, or if we had this much of A and excess B, how much of C would we make? Those are theoretical yield questions. So you can see that in the form of mass to mass, mass to volume, volume to volume, and you can also have limiting reactant on top of that. So you may be asked to calculate the theoretical yield as part of calculating the percent yield. The percent yield, you're looking at the ratio of the actual yield compared to the theoretical. This equation down here is what you'll need to calculate percent yield. Take the actual, divide by the theoretical, multiply by 100%. You'll be provided with this equation on the equation sheet for the final exam. You won't really need like an equation sheet per se, but I always like to post one at least with the study guide. Because we're doing 4 exams and we're not going to have a 5th exam for chapters 9 and 10, the final is going to be more of a chapter 9 and 10 exam plus some questions of old. And we'll talk about that once we get through percent yield. We'll also talk about exam 4 at the end. So stay tuned. Don't just log off. We got some family business to talk about. So first I'll show you an example of just a simple percent yield problem. Let's say that you perform a reaction and you obtain 0.875 grams of copper 2 carbonate. That word obtains lets you know that that's your actual yield. So you might see obtains, you might see produces or produced, gives, yields, anything like that, where you're saying that someone did an experiment and this is what they got. That's the actual yield. And it's spelled out pretty clear that the theoretical yield is 0.988 grams. We have to calculate the percent yield. This is our equation. You fill in the numbers appropriately. Actual yield, 0.875 grams. Theoretical, 0.988 grams. Multiply by 100%. You do want to, watch for sig figs here. We've got 3 sig figs in our actual and theoretical yields, so we should have 3 sig figs in our answer. You should get 88.6%. So here's my question to you. Do you want to do a simple example like this? Or do you want to try the more difficult problem where it's one of the stoichiometry problem types on top of a percent yield? So let me know, simple or hard. Which one do you want to try? Okay. Then I'll make sure that the answer to this one is in the notes, and I'll just note that we skipped it, so it's there for anyone who wants to try it. So here's the more difficult one. You can feel free to go ahead and try it on your own. I'm going to talk it through and walk it through while you do that. After combining 10.5 grams of iron 2 oxide with excess aluminum, 6.25 grams of iron were produced. What is the percent yield of the reaction? So let's write down what we have. We've got 6.25 grams of iron produced. So that sounds like an actual yield, which will be helpful because we need that to calculate percent yield. Then we've got 10.5 grams of iron 2 oxide mixed with excess aluminum. we need to figure out how much iron that would actually make. That's going to be our theoretical yield. For this problem, it's a stoichiometry problem. We're given a mass of starting material, and we have to figure out the mass of the product that we would make if we had 100% yield, which never happens. That makes this a mass-to-mass question on top of percent yield. I'm not going to write out the plan, but I will write out the full equation that you need to solve this problem. Let's assign our A and B. A is the iron 2 oxide. B is our iron. First, we get from grams to moles. And this is the same equation, chemical equation, that we were using several slides ago for the limiting reactant problem. So you already have all of these molar masses, if you were able to get it down in your notebook. If not, I apologize. The next step, we've got to write that mole ratio, and it's going to be B over A. And then finally, the molar mass of iron. Unit analysis. Make sure everything cancels, which I still do that to this day. It's not just to show, or, well, you should do it this way. I actually do this. When I pre-solve these problems, this is exactly how I do them out. I don't like to have to redo things. I don't like mistakes. So this way, I make sure that I get it the first time. That's how you put it into your calculator. And that would be your answer. But remember, we're not done. This is just the theoretical yield. Now we need to calculate the percent yield. Actual over theoretical, and you multiply that by 100%. We fill in our numbers. The actual we get from the problem, 6.25 grams. Theoretical, we just calculated, 8.16 grams. Do that division, multiply by 100%, and you should get 76.6% for your percent yield. Questions here? This is about as complicated as it gets. The only other thing that could be thrown at you is if there was a limiting reagent question. So you had to figure out how much figure out your theoretical yield and then do the percent yield. So if there's no questions, we're going to move on to the reminders. So your Mastering Chemistry for Chapter 9 is due this Sunday, and that's April 18th. We've got a final exam coming up, so there's no more regular exams. We just have the final exam, and that's going to be due Monday, May 3rd. It will be a take-home exam. I will post it a week before it's due, so you can start working on it ahead of time. We'll do some review in class as usual during the last week of class, and that'll be it.